Hello, my name is Sarah Foss, and I'm a graduate student in the Computer Science Department at UBC Okanagan. And in this video, I will be presenting the article, Linking Individuals Across Historical Sources, a Fully Automated Approach. This paper was written by Ran Abramitsky, Roy Mill, and Santiago Perez, and was published in 2019. In this article, Abramitsky and his colleagues outline their probabilistic method for record linkage with historical datasets. So first of all, I want to discuss what record linkage is. Record linkage is the process of matching records that belong to the same entities in different data sources, so it relies primarily on finding matches based on unique identifiers. Common identifying attributes might be social insurance or social security numbers, addresses, or other fields that are typically non-unique. In this example, we have two data sets that are linked very easily by the first column, which is a unique numerical identifier. However, it is not always so straightforward with all data sources. Linking individuals with historical records like censuses can be problematic because many historical data sources lack unique identifiers like social insurance numbers or social security numbers, and they actually may contain multiple individuals with non-unique names and ages. Historical records also tend to be prone to enumeration or transcription errors caused by human census takers or data entry personnel. It is very common to find spelling errors or other human error throughout a historical dataset. There has actually been a fair amount of research into this area, and there are numerous methods used to match historical records, although many of the methods rely on common sense matching rather than formal statistical methods. Or they tend to rely on hand coding, which is long and tedious and may not be fully replicable. Many times when two people are given the same raw data source and asked to hand link them, they will make different choices for the links, and therefore they will not generate the same training set. In this article, Abramitsky and his colleagues suggest a fully automated probabilistic method that uses standard statistical techniques that are widely used in non-historical settings for record matching and is fully replicable. Before we get into methods used in this approach, let's discuss the main problem with historical record linkage, the matching problem. Let's say we have an observation containing the name Sarah Foss in the 1890 census, and that record has her age as 20 years old at the time. Now we then query potential matches for Sarah Foss in the next census 10 years later, and we find five potential matches for Sarah. We find 4 matches that have the expected age to be 30 years old in this next census, but 3 of those matches have slightly different spelled names, and we have 1 other potential match that has the same spelling but has the age as 31 years old, which is 1 year older than expected, which is the correct match. It might be tempting to choose the exact match, but one of the other 4 matches may very well be the correct one, given that the human enumerators are prone to making mistakes and people may not report their exact ages but rather estimate it or round it up or down. So how do we go about solving this problem? One solution is to adapt methods used for record linkage in non-historical settings. Whenever we are performing record linkage, we have 3 main goals. First of all, we want to ensure that we're making as few false matches as possible, so we want to minimize those false positive or type 1 matches. Our next goal is to make as many true matches as possible, so we want to minimize false negative matches or type 2 matches. And our third goal is to create a sample as representative as possible of the population. Now, I'm going to go through the methods used for this historical record linkage approach, and I will break it into 3 sections. The first part of the method is selecting, identifying, and blocking variables, and then measuring string distance. Then, the next step is to assign probabilities that 2 records are a match. And finally, the last step is to actually choose the records that will be linked. First, the researcher needs to identify variables that will be used in the matching process. There are some common variables used in historical record linkage like name, age, gender, occupation, place of birth, or place of residence, to name a few. But really, the decision of the selection of the variables should be based on the research question. And the reason for that is that it almost seems intuitive that adding more variables will increase the true match rates and decrease the false match rates, but it may also introduce some non-representativeness in our matches. For example, a variable like occupation would probably appear in the census, and it could potentially increase true match rates and maybe even help us identify the individual. But what might happen is that if the person has switched occupations in the time between censuses, then it would exclude them from being a possible match. Next, the researcher needs to choose some blocking variables. If we compared every record in dataset A to every record in dataset B, that would require A times B comparisons, which is computationally infeasible for most datasets. What can be done to reduce the computational requirements of the method is to select some variables to block on. What happens when we use blocking variables is that records will only be compared if those variables' values are the same. So, in the case of the example on the screen, if the researcher chose to block on gender, then the record on the left would then only be compared to the records that have the gender specified as female on the dataset on the right, reducing the comparisons that need to be made on each record by half in this case. Because this will totally block consideration for some records as matches, it is very important that blocking variables should be chosen from fields where enumeration and transcription errors are unlikely to occur. The next decision the researcher needs to make is what method they would like to choose to measure how dissimilar two strings are to one another. There's actually a number of choices for calculating name dissimilarity, including many edit distance measures like the Levenshtein distance, which measures the difference in characters between strings, or there's also phonetic algorithms like the New York State Identification and Intelligence System, which assigns words with similar pronunciations the same phonetic code. To make a decision about whether or not to use an edit distance or a phonetic algorithm, there's a couple of considerations to keep in mind. When inconsistencies in names seem to result from hearing the name and writing it down incorrectly, a phonetic algorithm might be more useful in that case. And then when errors stem from incorrect spellings, an edit distance algorithm might be more beneficial. It is important to note that the two can actually be used together as well. The authors of this paper chose to use the Jarrow-Winkler distance measure, which is an edit distance measure, since it was developed for the comparison of names specifically in the context of record linkage. The Jarrow-Winkler distance measure is a variation based off the Jarrow similarity measure. To calculate the Jarrow-Winkler distance, we first need to start by calculating the Jarrow similarity, which is a straightforward similarity score based on two strings. This will return a number between 0, completely dissimilar, and 1, exactly the same. Once we have that, we can add the Winkler variation, which will then give a higher rating to two strings that match from the beginning. Then we can finally calculate the distance score with the inverse of the similarity score. Once the researcher has chosen all of the identifying variables and blocking variables and the string distance measures, the method can begin assigning probabilities to each of the possible matches. The authors of this paper used an application of the expectation maximization, or the EM algorithm, for assigning probabilities to each of those matches. This algorithm is commonly used in non-historical record linkage contexts, but has not been widely adopted with historical record linkage. What the EM algorithm actually does is it will estimate parameters where there is some unknown data. In this case, the unknown data is whether the records are matches or they are non-matches. To explore the expectation maximization algorithm, let's look at some simulated data. Here, there have been 100 age distances simulated. The distances that are true matches are drawn from a normal distribution with a mean of 0 and a standard deviation of 1. And then the distances that correspond to the non-matches are drawn from a distribution with a mean of 5 and a standard deviation of 1. We can see in that first figure that the matches are colored in red and the non-matches are colored in blue. But the problem is, we actually wouldn't know if these observations were matches or non-matches. So in the second figure, there the data points are all colored the same color, purple, because we didn't know which group they should belong to. So the goal of the algorithm is actually to estimate the probability that each of the distances are actually a true match. So how the algorithm actually works is that it's going to start by assigning a distribution for each group, and then it will estimate the parameters of each distributions. So it will estimate the probability of each group and the mean and the standard deviation of each group. And then it will use the parameter estimates to identify two separate clusters. It will repeat the estimation and the clustering until convergence, and then from there, we can see the probabilities of each observation being a match or a non-match. Let's go through the expectation maximization algorithm step by step. First, let's go through some definitions. We're going to say that A cross B is a set of ordered pairs of records. Then we're going to say that the set of matching records is represented by M, and the set of non-matching records is represented as U. The distance of each observation is represented as gamma I, and the vector holding parameters mu and sigma is represented as theta. Now to go step by step through the expectation maximization algorithm. First, we're going to define a distribution family for the probability of each observation belonging to the true match group or the non-match group. Then, we're going to guess the initial mu and sigma for each group along with the unconditional probability to be a true match. Then, we're going to loop over steps E and M until convergence. The E step is where we're going to calculate the expected value of the probability of an observation being a match, given the distance and the estimated parameters and the conditional probability of being a true match. The M step is where we will estimate the parameters using the maximum likelihood estimation, which we will find the parameters that will maximize the likelihood of getting the data that we observed. Once that's done, after convergence, we will then be able to quickly compute the estimated probability of an observation being a true match. The last step in the method is to choose the records that are to be linked. So one approach, which may be more intuitive, is to choose the match with the highest probability of being true. But unfortunately, there's actually several problems with this approach. First of all, the highest probability might actually be quite low, so we may actually not even want to make those matches. And then, even if the highest probability is very likely, there could be a second best match with a very similar probability, so there may be some ambiguity as to which match is correct. A better option is to set the following decision rules. For any record in dataset B to be considered a match with a record in dataset A, it must satisfy three conditions. Number one, the record must be the highest probability of being a true match out of all the potential matches and dataset A. Number 2, the match must have a probability that is higher than a given threshold P. This threshold is set by the researcher and is somewhere between 0 and up to and including 1. Number 3, the record must have a second best match with a probability that is unlikely. That is, a probability that's less than another given threshold L, which is somewhere between 0 and P. Also, for a record in dataset A to be a match with a record in dataset B, the same rules must also hold. The question then becomes, how do you choose the thresholds P and L? By using different values for P and L, it's actually possible to generate matches with more or less confidence. Higher levels of P and lower values of L will result in fewer links, but those matches may be of higher quality, which may decrease our false positive matches. Conversely, lower levels of P and higher values of L will result in some matches having a lower probability of being a true match, but more overall matches, which may decrease our false negative matches. Now that we have gone through the methods of this approach, let's look at it in practice. Abramitsky and his colleagues tested their method and compared it to a widely used method for historical record linkage from IPAMS, which is part of the Institute for Social Research and Data Innovation at the University of Minnesota. In their application, the authors of this paper used two different sets of data. They looked at white males from the U.S. based on the 1850s to the 1880 census. And then they also looked at males from Norway based on the 1865 census to the 1900 census. For their variable selection, they chose to use the attributes first name, last name, place of birth, and predicted year of birth. They chose to block their data by only matching records where there was the same place of birth, the predicted age difference of no more than 5 years, and the first and last names had to start with the same letter. For their threshold selections, they actually went with two different sets of values. One, which was less conservative, set the P threshold to be 0.6 and the L threshold to be 0.3. And then the more conservative values set the P threshold to be 0.7 and the L threshold to be 0.1. Though they compared their results to IPAM's linking method, their linking methods were not entirely dissimilar. Both methods identified a set of potential matches for each record and created name and age similarity scores. The major difference between the two methods is that IPAMS created a 1% training sample of manually classified records and then classified the rest of the matches with a machine learning tool called a support vector machine. The resulting samples of both methods were compared to the actual population using non-linked cross-sectional census data to verify that they represented the population. As you can see from the figures, which plot the occupational structure of the fathers from the initial census year, the samples were not identical to the population. However, they were very close, suggesting that both methods actually produced good representative samples. Finally, they used their samples to compute rates of intergenerational occupational mobility, or the rates at which sons held different jobs from their fathers. Both methods produced very similar tables with both the U.S. and the Norwegian samples. As you can see, the estimated percentage of sons in each occupation, even across skill level, is very similar. Overall, while there are small differences in the matrices, the evidence indicates that both of these historical record linkage methods produce very similar results, showing that the author's fully automated probabilistic approach is comparable to the widely used IPAMS method, which requires hand coding. Furthermore, this method is relatively straightforward to implement, and the resulting samples are easily replicable. Thank you very much.